Hello and welcome to my demonstration here where I'll be trying to solve for a line of best fit with some experimental data. So let's get started here. All right. So I will be doing it in Python, specifically Colaboratory here, and I'll be starting a new notebook. So our experimental data here is from our professor's GitHub site. So I'll be getting that. It's this water vapor pressure .csv file. And we want the raw here just so that we only get the values, right? We're only getting the values. So this is our experimental data. So we have to bring it in here. So the way to do that is to use a command, and it's not a command in Python. So to denote that, we'd use an exclamation point, and it's called wget. And it gets, using a web address, it gets whatever data you have. So let's get that web address for this file, for this data. So there it is. I'll shift enter, and it has successfully obtained that. Now, we want to use this data, right? So let's store it somewhere in a variable, right? So data will be stored as, I'll have it as data. And actually, before that, the function that we need to use comes from a library in Python called numpy. So we need to actually bring that in there. So now that I've imported it, we can actually use it. So it's something called load text. And it needs some parameters like the file name. So water vapor, and there it is. Tab it in. .csv. And since it is a string, we need to put apostrophes here to denote that it's a string. And another thing that this function needs to work is it needs to know how these things are separated. It's delimiter. And in the name, it's delimiter is a comma. So we need to also denote that. Oh, oops, comma. Shift enter. And now we have our data loaded. 2.93. There it is. All right. So our raw data here given to us is actually two separate types of data. On the left side here is actually temperatures, and our right side here is actually pressures. So let's separate the list, right? We need to use our temperatures, pressures. So let's start with temperatures. So I will label it as T. So our temperatures inside the data is all the rows, which is denoted with a colon, all the rows in the first column, which in Python, the first index is 0. And we can test it out. Here's our T, temperatures, right? 293,303. 293,303. So we successfully imported that in. We'll split the list, right? Now we can do the same thing for pressures, right? So same exact thing. Pressures in the data. In data is all the rows in column 1, the next column. And we can also check, right? That's been properly loaded in. And as we can see, 2.4, 4.26, 2.44, successfully loaded in. And now we have our data, right? And now let's graph our experimental data, right? I'm trying to find a line of best fit. So I will be using plotly.subplot to make my subplots here, to graph my data. So I'm going to import make underscore subplots. And this is just a preference thing, but I also import plotly.io, and I turn the background of my graphs into a darker theme. This just makes the data a lot easier to see, and it looks better. So to do that, po.text templates dot default equals plot v underscore dark. All right, shift enter. And now that's loaded in. So let's get to actually making our graph with our experiment data. So I have imported the function makesubplots. Now that's a lot to type over and over again, right? So I can assign it to a variable, and I can use that variable instead to pass through the commands that I want to do. So there we go. So let's actually make our data. So the function will be add underscore scatter. That'll make us a scatter plot, right? And our x values will be t, and our y values is going to be pressure. And it is experimental data, so it would be best to make it look as if they were dots. So that would be mode markers. There we have it. Now these values are humongous, right? We want them to be easier to work with if we were to ever do something with the data, right? And one way to do that is to change the y-axis in a way, or y data. And the one specific way I'm going to be doing it, there's a reason for it, is I'll be changing it to log base 10. And it's super easy to change the data over. We would use the log 10 function from numpy and simply just log base 10 all the values in it. There we have it. And then we just have to change this to our new y. And super small values, a lot easier to work with, right? So how would we even go about to starting to find the line of best fit for this, or in this case, a curve of best fit, right? Well, you see, these temperature and pressures come from a phase diagram. And these temperature and pressures ride along this line here. And there's actually a specific equation that relates the two, and that is Antoine's equation. And so that's the equation that we will be using to hopefully find the line of best fit. So first off, we're going to try a nonlinear method. And that method is going to be minimizing the squared sum error. So squared sum error. Well, let's say for now, let's imagine that we have some curve going through the data. All right, not a perfect one, not the best fit, just some curve. Well, between the distance between that curve and the experiment data is called the error. And let's say it's not a good curve. All right, let's say it's over all the points. Right, so bunch of error. And well, to find the total error, we'd sum it all up, right? We'd sum up all the error, and we'd have this total error showing how bad our line is, right? It's obviously not the line of best fit or a curve of best fit. And so what we do is, try to minimize that. So then let's say we have a curve that's has experimental data above and below. Well, we have some issues here, right? Well, we have some positive errors and then some negative errors. So that's where the squaring comes in. So that we're summing all these squared errors so that we get this actual total positive value. And then from there, that's what we're trying to minimize. We want to minimize that sum squared error so that we actually have a best fit that goes through this, a perfect curve. So let's do that, right? And that's one of the main reasons why I did the log base 10 for the pressure values, because in Antoine's equation, the pressure in that equation is log base 10. So let's get to solving this. So let's make a function, which we'll need later. And it'll be called the sum squared error, right? And we want to pass some values through. So sum squared error. So it's the function of the curve, right? Those values minus the values of the experimental data. Well, what values are we comparing? It's the pressure, right? So in Antoine's equation, how do we find that pressure? Well, the function itself is a minus b over c plus d, right? And so we already know what temperatures, right? So what we're missing are the a, b, and c's. So this function that we're making will take three values, a, b, and c. So we know that this function is going to take three values. So we have v0, v1, and v2, right? We could put that way. Or since we know what the three values are, a, b, and c, we can sort of set it as those variables beforehand. We can unpack the values that we obtain that the function calls for and unpack it into those variables because we know that those values will correlate to these variables. So we can do that as a, b, c equals the values that are put in, the list that is put in. So we can do that. So now let's get to actually building the error, right? So like I said, how do we find the pressure value? Well, it's Antoine's equation. It was a minus b over c plus t. And to find that error, you subtract it from the experimental pressure, right? So that's just simply log 10p. And to negate the negative values, right, we want to square that. And then we're finding the sum. And to find the sum, it's simply using numpy's sum. Now, we want to get a value from this sum squared error, right? So we want to return it. We want the function to return a value. So we do that. And now that is complete. And like I said earlier, we're trying to minimize the sum squared error. So how would we go on to about that? We have our function, our sum squared error now. Now we just need to find a way to minimize it. And Python, base Python at least, does not have that. So we need to import a function from SciPy, their optimized library, and we're going to be importing their minimize function. And now we have what we need to minimize the sum squared error. So minimize, and now it needs a function, which we just made, SSE, and now it wants us to give it a guess on what the ABC values are going to be for the curve of best fit, right? So I don't know what those values could be, so I'm just going to give it probably a really poor guess, and I will evaluate it. And here we have it. It has found the best A, B, and C to give the most minimal sum squared error. And that's what we have all the way down at the bottom here. Now, seeing this function gives us a bunch of different properties here. We only want this last one. So there's a trick that you can do called put .x and it'll just show the .x, which is the three values that we saw earlier. Well, we know what these three values are, right? It's A, B, and C. And so since we do that, we can apply the same unpacking method, and that is to give them variable names. And there we have it, A, B, C. Well, now we have the best A, B, and C for a line of best fit for our experimental data. So let's plot it. I will note this as experimental data and this as our non-linear method. So fig scatter x equals t, y equals our Antoine equation, right? A minus b c plus t. And well, we have our newly a, b, and c values that is best for this function. Right? We now have the right coefficients for this function. And the mode will be lines. And here we have it. But you might notice something. It's a function, right? It's supposed to be curve-like. And what we see here is sort of jagged. And that's because we're finding values for the experimental temperature points, right? So it's kind of jagged. It's going from point to point. And there's a simple fix to that we can do. And we got to realize that the Antoine equation is a function, right? So it should work for all temperatures, all x's. And we can do that. We can give slash make our a function a bunch of x's that would end up, make it look smooth. So we can set a variable here, temperatures for plotting purposes, a bunch of temperatures, and we'll be using a function called Linspace. And Linspace here will give us equally spaced points between a given start and stop for a number of points, right? So let's see here. We want it to be between our experimental data, right? So let's do something like 273, stop at 650, and we want 100 equally spaced points. I can shift enter that in. It's now, and now we can change our x here for our nonlinear to our temperature for plotting purposes. And we wanted to evaluate those x's, right? Now we have it. This curve that should be the best for the data, experimental data. Now, surprisingly, you can actually find a line of best fit using a linear regression method as well. So, linear regression, right, is where you have a design matrix, right? And you multiply it with a vector of unknowns that equals a vector of knowns. Well, you want to set up in a way where you have this linear equation for your first set of data points, and then you multiply it with your unknown coefficients, and you get the answer for your first data points, right? So you wanna set it up in a way where you're solving a system of linear equations with its supposed answers, and you do matrix multiplication with this unknown to get those answers, and it solves for these unknown, right? So we need our linear equation, right? Well, we've been using Antoine's equation, and the first thing that might come into mind is that, well, Antoine's equation here, log 10p equals a uh, minus b over c plus t is not exactly linear, right? So that's our first step, actually, is to rearrange this equation so that it looks linear. So let's do that. So first we want to get rid of the c plus t, right? The fraction. So we can multiply c plus t across, and we would get c plus t, quantity, right, times log 10p, that equals the quantity c plus t a minus b. That looks a little bit better, right? But we can go further. So let's distribute it, right? C log 10p plus t log 10p equals ca plus ct minus b. So right now, we have it set up this way, which is quite linear, but we want to set it up so that it's like our framework here, right? Linear equations, where we can multiply it with our unknowns in this vector, and we get our knowns. So let's separate it into our unknowns and knowns next. So we can move all three of these actually, all we'd have to do is move this over to the right, right? So let's do that. So we would have CA. Actually, I did that wrong. This should be AT. My bad. So we would have AT. Uh, oops, lost my pen. Minus C log 10p plus CA minus B equals T log 10p. Now we have our unknowns and knowns, right? So our known is T log 10p. Well, for our first temperature and pressure, right? And well, we can start filling in our design matrix here. Well, we have T1, right? That would have to be multiplied with the unknown A. Then we have C. That would be times negative log 10 P1, right? And then we have this CA. How would that work? Well, thing is, it wouldn't work. And well, we can try skipping it, right? Well, B. Well, we would put in a bunch of negative ones and put B here. Well, that doesn't work out because then we still need CA. So we have an issue here, right? We have this sequence that we need to take care of. Otherwise, our system's equations wouldn't work. So there's actually a pretty simple solution for that, right? We can just turn this into another variable. U equals this entire thing, CA minus B. So then we have our third unknown, U. And, well, that's just a bunch of ones for a seemingly infinite amount, right? Seemingly infinite amount to n experimental data points. And, well, that's the issue right now. We have n amounts of data points, right? And so moving on to a different page here, right now we have this matrix. I'll write that somewhere else here. Matrix that is right now a n by 3. It's kind of infinite. And well, it's being multiplied by this vector that is currently a 3 by 1, right? And it's resulting in a, say, result of a n by 1, because we have n amounts, an infinite amount of experimental data points right now. And well, you can't solve for that current, right? So a way to sort of make it possible to solve, right, is to multiply the transpose of the matrix to the original matrix and the result, right? Let's pretend that's matrix multiplication. And so we would have a 3 by n, and these would cancel out to make it a 3 by 3, right? And this is a 3 by n, right? And this would cancel out. And that would make it a 3 by 1. And that's, well, that's exactly what we need to end up to solve for a 3 by 1 vector, right? 3 by 3 times a 3 by 1 can make, you know, a 3 by 1. And so that's how we solve for this using a linear regression method. So let's do that in Python, right? So let's do it. So let's make our matrix, right? Our design matrix that we had earlier, which is this. So we want to concatenate 3 different lists together to make our matrix, right? And so we would have the t's that we saw earlier. We would have the negative log 10p, and then we have our ones. Well, how do we get ones? We want it to be the same size as our other variables here too. So there's a function for that. It's called np1s, like the same size as t. We could do either, but just that we don't have to type as much, we do T. And well, what do we do with that matrix now? Well, the next thing we do is, well, do some matrix multiplication with this transpose. And we multiply that by the vector, and we get the transpose again of the matrix time, and that would result that, right? So we have our two things to solve for the unknowns. And there's a function in NumPy that allows us to solve for it. And it's called linear algebra, linalg.solve, and requires the design matrix here. And this our results as our argument to solve for our vector. So that's how we'll put it in. So M transpose, right, matrix multiplication, which is denoted with an at n, and the second argument, which is the results, right, m dot t at, and well, our result, which result is, well, this. This is our result. Temperature times log 10p. Temperature times log 10p. And we can solve that. And well, here it is. Here are three values. But remember, A, C, and U, because that was our unknown that we found here. So how do we solve for U? Well, it's easy. Well, U equals CA minus B, remember? And that's simple algebra. We just move the B over and the U over, and we have it. And before I do that, we can do the similar unpacking method that we did earlier. LC and U equals the three values that is solved.
Like I said, it's LA times LC minus U. And let's check out those values too. And compare it to the nonlinear A, B, and C. And as you can see, they are very similar. Similar enough, right? And as you expect for a line of best fit. So let's plot it here. And exact same method as earlier for the nonlinear. Doesn't change. X equals, well, the temperatures we're plotting. Y equals, this time, LA minus LB over LC plus T plot. And we want the mode to be lines. There we have it, and as you can see, they very almost overlap each other, but obviously the values weren't the exact same, right? So they wouldn't exactly overlap, but they're very close, right? From this point of view, they're basically overlapping. And that makes sense. They're lines of best fit. They're curves for this data. So that was me solving for a line/curve, in this case, best fit for the experimental data given.